Hey there, all you crazy cats and kittens. Hopefully you've seen Tiger King, otherwise I sounded like a total weirdo. But we're going to go ahead and finish up chapter 22 in this video. Right, so we've got three reactions that we're going to be looking at today. And the first one is the Claisen condensation. And yes, this is the same Ludwig Claisen that we saw in the Claisen-Schmidt variation of the Aldol reaction, but nonetheless there's another Claisen reaction that we're going to be looking at, and this is the Claisen condensation. And the essential reaction here is that we're going to take an ester plus an ester, and it's going to give us something called a beta keto ester. All right, so what we're going to have here is a reaction of two esters. All right, and this reaction works best when you're dealing with two of the same esters, or one of the esters is enolizable and the other is not. So let's go ahead and look at an example of taking two esters that are the same. And before we get into those esters, I just want to kind of recap some nomenclature here. When we use the symbol ET, that is ethyl. All right, and Me is methyl. So these are alkyl groups, and we'll often see esters using these abbreviations. So something like ETO, specifically with an O minus. This is called ethoxide. And this is the conjugate base of ethanol. All right, as would this nomenclature suggest, this would be methoxide. And this is the conjugate base of methanol. All right, both of these are pretty strong bases, especially in an aqueous environment. But they're not as strong as the lithium amide bases that we saw previously. So these are going to generate thermodynamic enolates, but they're still relatively strong, and they'll work well enough to deprotonate an ester. All right, so just to recap, ethoxide and methoxide are some of these bases that we're going to see a lot in the following reactions. All right, so let's get started here. Let's look at an ester. This guy right here, and this guy is called ethyl acetate. All right, this is a very commonly encountered ester. It's a solvent. It has a very familiar smell. Any of those that have been in a nail salon, and you know, it's used a lot in makeup removers and so forth. So it's a very commonly used solvent in industry and in day-to-day life. All right, so if we react it with another molecule of ethyl acetate in the presence of a base, and the base that's commonly used is an alk oxide that matches the leaving group on one of the esters, in this case both of the esters. All right, you would not want to use methoxide in this reaction, because what you're going to get is a transesterification, and it's going to lead to a mess. So short story, make sure your base matches your alkoxy group on your ester. All right, so we have ethoxide, and our alkoxy group on our esters is ethoxy. All right, so our product will be a beta keto ester, and we're going to go through this mechanism and show you how we get to this. All right, so here's our beta keto ester, and we call it that because in green we have an ester. All right, and then we have an alpha carbon here, and then if you were to imagine the next carbon being called a beta carbon, well, at that beta carbon we have a ketone, thus we call it a beta keto ester. All right, so that's how we that's the product we're going to get from this reaction, but what we need to see now is how in the world we get there. All right, so it's a very similar reaction to what we've been seeing in the past. So I'm going to put one ester in green here, and another ester in, let's do red, look Christmassy. And I'm going to put my ethoxide in yellow. All right, so the first thing that's going to happen is we're going to form an enolate in a reversible fashion. Okay, so we're going to take the proton off the alpha position, and this is reversible. So what we get is an enolate, a thermodynamic one. We still have our green ester. Oops, need to make sure it's an ester. And now we have generated ethoxide, and let's see how we do by keeping up with these colors. All right, so the next step is going to be nucleophilic attack of the enolate on the green ester, which has an electrophilic carbonyl. So that arrow push will look like so. All right, and this is reversible. So now we just need to keep track of everybody. All right, and much like in the aldol condensation, what we can look at here is this was our alpha carbon, and the carbonyl here we're going to call carbon A on the green ester. All right, so we'll go ahead and draw that out. See, I need red. So there's our alpha carbon. And we've bonded to the green carbon. All right. Okay. So everybody's accounted for now. And what we're going to do next is we are going to grab this left out a very important group there, the methyl group. All right. So now what we're going to do is have the tetrahedral intermediate collapse. All right, so what we have here is this carbon, which I'm highlighting with the green dot, is a tetrahedral intermediate, and it's going to collapse by kicking off a molecule of ethoxide. All right, so this is a reversible step, and we need to move on to the next page. Here. And what color did I use for the ethoxide I kicked off? All right, so I've got ethanol and ethoxide. And I have my beta keto ester. However, it looks like we're done, but the problem is we have a beta keto ester, which has a very, very low pKa value. All right, that pKa value is probably somewhere close to 11. And we're going to imagine that if it's 11, that it's got an alpha hydrogen that is very acidic relative to ethoxide. All right, so the ethoxide is going to grab that hydrogen if that beta keto ester is ever formed in solution. And since the keto side is more acidic than the ester side, pardon me, we're going to resonate up through the ketone. All right, this is just a a small detail. It really doesn't matter whether you resonate up to the green oxygen or the red oxygen, but it's just semantics. It's going to go up to the keto because it's easier to resonate up through there. Okay. And now we have 2 molecules of ethanol. And the reaction is going to stop here. And pardon me, this last step here is not reversible. It's irreversible. And the reason why is the severe difference in pKa values. Remember I said the pKa, the beta keto ester, is somewhere around 11. And the pKa value of the ethanol is around 18. So we have a very large difference in pKa values. So this is almost a one-way street to the conjugate base of the beta keto ester. So this reaction is not going to go anywhere until we do what we call an acid quench. And once we have an acid quench, we're going to put back on the proton to give us our beta keto ester. All right, so quite an involved mechanism, but with some practice, you should be able to get it. All right, you just need to watch where your pKa values are falling, all right, and keep track of your carbon-carbon bond forming reactions, and you'll get it. All right, so the Claisen condensation is a reaction that has a complicated mechanism, but I think one that you can certainly handle. All right, so let's take a look again at some examples so we can practice these. All right, so if I'm looking at the textbook right now, they have a reaction that shows an ester like so. Okay, so they're taking 2 identical esters, and if we look here, this time it has a methoxy group on it rather than ethoxy. So we definitely want to make sure we're using the right base here, which is going to be methoxide. All right, so how can we imagine that this reaction works? Okay, so the way I like to look at this is I'm going to draw an alpha here, and then I'm going to draw an E here. All right. The reason why is I'm going to say that the alpha is going to attack that electrophile. All right, so I need to make a bond between those two. So when I do that, so there's my alpha, and here's E. All right, so what is E going to have on it after it gets attacked? An OMe, a pH, oops, sorry, a CH2 pH, right? 1 carbon to the pH, okay? And then we have our O minus. So convince yourself that's what you're going to get, all right? Work on the mechanism for that first step and see if you arrive at the same thing I do, all right? So the next thing that's going to happen is going to be the collapse of the tetrahedral intermediate, all right? And what's going to happen here is this guy is going to kick off our methoxy group, and I wind up with my beta keto ester. So I'm going to redraw it. Let me try to shrink up my arrow here so I can fit it in a little bit better. So there's alpha, E, all right. E is now a carbonyl that's collapsed to kick off the methoxy group, and I'm left with a CH2 pH, all right. So that's how we rationalize our product. Okay, so you see how alpha and E have connected. So practice that one and see if you can come up with the same product, whether it takes going through the mechanism and then convincing yourself how alpha and the E carbon connect to each other. All right, so that's the Claisen condensation. The next one I want to look at is a little more straightforward. It is called the, actually no, don't want to jump ahead yet. We're going to look at the intramolecular Claisen condensation, which bears the name of another scientist. It's sometimes called the, I'm actually not sure of the pronunciation here. I think it's called the Dieckmann condensation. But it's simply an intramolecular Claisen condensation. All right. So we can do this with something called a 1,6-diester. So if we look here, one, two, three, four, five. Did I get that right? 1, 2, 3, 4, 5, 6. Yes. This is called a 1,6-diester. All right. And if you notice, it is a molecule with two esters on it, hence the name diester. But it's large enough to where it could do something called a annulation, which means it is a reaction that takes a acyclic molecule and forms a cyclic molecule from an intramolecular reaction. So that's a fancy word, annulation. It just means it is a cyclization of an acyclic molecule. All right. So how does this work? Well, it's going to work through the Claisen condensation. So let's go to a fresh new page here and look at our ethoxide diester. And there's 6. And since we're going to undergo a Claisen with a diester, we need to match the base. So there's our ethoxide. And we need to pick off a proton from an alpha position. All right. So it really doesn't matter which alpha position you use because they're identical here. All right. But again, if you had the choice and you wanted to make a thermodynamic versus a kinetic enolate, you're always going to go with the thermodynamic here since you're working with ethoxide. All right. So in this case, that doesn't matter. So I'm going to put an alpha hydrogen there at carbon 2. And I'm going to form this enolate. And this is a reversible process. So now I have my enolate. On carbon 1. And I have a double bond between carbons 1 and 2. Then I go to 3, 4, 5, and 6. All right, this guy is intramolecular, which means the reaction is going to happen within the molecule. So we're going to collapse this way. And now carbon 2 is our nucleophilic carbon that's going to go after carbon 6, which is our electrophilic carbon. All right, so we're going to form a bond between carbons 2 and 6. So what we need to do, since we have everybody numbered, is figure out how large of a ring we're going to make. So I'm going to put dots and count. So that's 1, 2, 3, 4, 5. 5 carbons are going to be formed in this ring forming, or be members of this ring. Why not carbon 1? Carbon 1 is going to be a carbonyl that is outside of the ring. All right, it is not involved in the annulation process. All right, so what we're going to get now is a 5-membered ring, and we need to number this ring. The way we'll number it is we'll put this guy 2. All right, and now we have to ask, what did 2 make a bond to? All right, look at our arrows. 2 made a bond to 6. All right, and then 6, of course, is bonded to 5, and then 4, and then 3. But where the heck does number 1 go? Again, it's bonded to carbon 2, but it's outside of the ring. All right, so it's out here. And what does carbon 1 have on it? It has a carbonyl, and an ethoxy group. All right? And what we're missing is the stuff on carbon 6, which has an ethoxy group and now an O minus. So here's our tetrahedral intermediate that's going to collapse, expel the ethoxide, and give us our beta keto ester product, like so. All right? So it's beta keto ester because if I look at the ester group, there's my alpha, all right? And in position beta is a keto group. So this indeed is a beta keto ester. All right? So a 1,6 diester undergoing an intramolecular Claisen reaction gives us a 5-membered beta keto ester. What would you imagine a 1,7 diester would give us? Yep. Hopefully you got 6-membered ring. I feel like Dora asking questions to nobody, but you guys are listening, I hope, right? Okay, so that's the end of this video. All right. I will come back with a new one right after this that's going to go over what we call the Michael reaction and the Robinson annulation. All right, thank you very much.